Okay, next up is dilations, but let me try to elaborate a little bit more about what we just discussed, the translations, and then we'll move on to dilations. Uh, think about the following: x squared plus y squared equal to 1. This is not a function because if you draw the graph of this, it's a circle of radius 1, centered at 0. Why is this not a function? Yeah? The vertical line test. If you use the vertical line test, it meets the graph twice, therefore it's not a graph of a function. However, we can still think about the translations you can apply to this. So think about the following. If I did x minus 2 squared plus y squared equal to 1, what would happen to this graph? Yeah?
Move to the right.
Move to the right by how much? 2. So you're going to have 1 and 2, and that will be the new center because before the center was 0, 0. If you move 2 to the right, 2, 0 will be your new center, and that will be your new graph. Okay. This is the graph of this equation. It's not a function, but it's an equation. The equation has this graph. Now, here's a twist. What if I do x squared plus y minus 2 squared equal to 1? What would happen to the graph? Any ideas? Just say it.
Would it be an oval?
No, it's still moving.
Get bigger.
No, it just still moves. It's still a translation. Translation means it just moves. It doesn't change its size.
Goes to the left?
No, you're doing something to y.
Down?
So it's either down or up. Okay. Let's,
Oh, yeah, 'cause it's Y.
okay. Let's do a quick poll. How many of you think it's going to go up? Okay, I see 3 people. How many people think it's going to go down? I see 7 people. Okay, the 3 who raised their hand is correct. It goes up. It goes up. Right? It goes up by 2. 1, 2. Just like that. Okay. I'm not making it up. You actually can plug in values to see which points satisfy this equation, and if you start plotting, you'll see that the graph actually goes up by 2. It's really strange. But the thing I'm trying to point out here is, how do you go from here to there? What's the operation being done here? What's the operation?
Foil.
No.
You gotta foil the y minus 2.
What I'm trying to say is that y is being replaced by y minus 2. Right? Okay. So the important thing I'm trying to point out is that y is being replaced by y minus 2. So this is a replacement of variable. Okay. So here's the upshot. What am I trying to teach you here? The important thing that you observe when manipulating equations and seeing their graphs is that whenever you do a replacement of a variable, the graph will act the opposite way, right? You subtracted the 2 in the x direction. It's like, oh, well, that means it should be moving left. No, when you actually draw the graph, it moves right. You subtracted 2 on the y direction. Oh, that must mean that y would be subtracted by 2. No, actually, if you draw it, the entire thing goes up by 2. It does the opposite. Okay. Now, knowing this is such an important point that I hope you get it, because if you get it, then everything that I'm going to teach afterwards just makes sense and it's easy. If you don't, then it will totally not make any sense at all. All right, so think about this. What would happen if I do x over 2 squared plus y squared equal to 1? Okay, from here to there, how do you get to here?
Divide, change x.
You're replacing x by x over 2, right? So would the graph act as it is, or would it act the opposite way? I said every time you do replacement, it will be opposite. So what's the opposite of taking half?
Multiplying by 2.
Multiplying by 2. So what do you think the graph would be?
Yeah.
Doubling what?
3.
So you had this graph,
Yeah.
doubling in which direction? X is being replaced, right? So you take this, think of this as drawn in a rubber band, rubber plate, and you do this, you stretch it, and then you get an oval. That's the graph that you get. Right? Okay, so let's try the following. What if I do x squared plus 2y squared equal to 1? What happens?
It's half
Through the y.
divides it.
Divides it by 2. So if this is 1, you squeeze it, right? Squeeze it like a lemon. Just like that. This is the graph that you get. 1, 1 half, negative 1. No, negative 1 half, negative 1, okay? So that's how you get dilation, okay? So these are the dilations when you have a circle like that. Now, I haven't shown you the dilation for a function yet. So let me show you a dilation for a function. For functions, there are two kinds. There's a manipulation of the variable, replacing a variable, or you can directly apply something to the function. So here's y equal to x squared, our favorite function again. And let's think about y equals to 2x squared and y equals to 2x squared. Hopefully you know that there are difference between the two, right? Because the order of operations, which one do you do first? Square first and then multiply by 2 first? Square first. It's this squared and then you multiply by 2, okay? All right, so this one, to go from here to there, what are you doing?
Replacing x with 2.
Replacing x by 2x. So what's going to happen?
Divide by 2.
Divide by the opposite. Whenever you divide, it's the opposite. So this divides, you squeeze, and you get something like this, okay? So if it passed through 1, 1 before, now it's going to pass through 1 half, 1. Okay, what about this? Are you replacing x by 2x? No, that's not what you're doing. What is this 2 being done? This 2 is multiplied to the function, right? So in other words, if you have y equals to f of x, what this is doing is you're multiplying 2 to the function. Whenever you do an operation of a function, then it will behave as you would expect. If it's doubled, it doubles. The value will double. If you add 2, the value will go up by 2. If you subtract 2, the value will go down by 2. So here, you doubled it. So what's going to be the effect for the graph? It'll be a parabola, but what do you do? Do you stretch or do you squeeze?
It'll be y.
Stretch in which direction?
Horizontal.
Up, stretch this way, because see, it's modifying the value of the function. Value of the function is y, right? So what you're doing is you're taking this and you're stretching this way. So you have this. Let's say this is the original one. Then you stretch it up, and you end up with this as your true graph. So what happens is that this 1, 1 will now be at 1, 2. All right. Did you get it? Did that make sense? Modifying the function does what? The graph would behave as you would expect. Modifying the variable does what?
Opposite.
It'll do the opposite. Now, can I do something that might make you a little confused?
Sure.
Okay, all right, so here's a challenge. If I do y divided by 2 equals to x squared, what am I doing? Am I modifying the function or am I modifying the variable?
Function.
No, I'm replacing y by y over 2, right?
Yeah.
Yeah, if I take y and replace by y over 2, this is exactly what you get, right? So what I've done is I've replaced the variable. So the graph will do the opposite. What's the opposite here? By 2, right? So again, you have this original graph, you stretch it twice and you get that graph, okay? Which is exactly the same as that, right? But now, do you see that that's actually same as this?
Yep.
Yeah, if you multiply by 2, it's the same thing. So of course they have the same graph. Okay. Yeah. All right. So although I explained that this is not replacing the variable by something else, but if you divide by 2, you can view it like that. Okay. You could view it this way. Okay. So it's still, although even if it looks like I'm saying something totally different here, I'm still using the same kind of philosophy. If you didn't understand this last part, that's fine. Just the important thing is you remember that replacing does the opposite to the graph, and doing something to the function will do exactly what you would expect.